Good day, Matric. This may be our last pre-recorded video for a while, so let's get straight into it. And I want to go to share screen, and I want to go to that. Right. So in this lesson, okay, I've sent you these notes. Okay, we're looking another calculus application, and I don't know why I've still got a shadow here. It's a banana. Finding maximum and minimums using calculus. This is often called calculus of optimization because you want to maximize or minimize things. And for me, the key idea is that any equation, okay, for any kind of subject, it doesn't have to be x and y, okay, any equation, okay, can be maximized or minimized if the gradient is equal to 0. So for instance, say you wanted to maximize income or something, money against time, and you could get some kind of equation which gives you, so you could have f of a function of time gives you money, right? In other words, like, I don't know, t cubed plus 3t squared minus 4 is equal to how much m of t, we could call it, the amount of money you're getting after a certain time. So if you get a function that represents two variables, okay, the one variable, the dependent variable, can be maximized or minimized. And when they're going to, whether you're maximizing or minimizing it, okay, that's going to happen just like if you think of a graph, when the gradient is equal to 0, okay, that's when your maximum is going to occur. So in other words, what gives you a gradient, okay, well, in this case, if we called this thing f of t, it would be when I've got to find out where f dash t is equal to 0, just like you found stationary points and turning points before. So whenever you see a question which says to you in paper 1, go maximize or minimize, maximize an area, maximize your income, okay, whatever, minimize the number of cases of an illness or something like that, your key idea in your head, think, well, if I had a graph, okay, of one thing against what I'm trying to, this is what you're trying to maximize or minimize on the y-axis, okay, if you had a graph, how would you find that maximum minimum? When the gradient is equal to 0. They won't give you a graph, they'll just give you the actual scenario, but think of it in your head as being a graph, right? So to do these kind of application questions, this is how I think of it. The first step you need to do is you need an equation for what you're trying to maximize, okay, or minimize, I should have said, maximize or minimize in terms of one variable only. Okay, you can't do at this stage of your life, it's full maths, okay, differentiation with more than one variable. So the first step is going to be, I have to get a function, for instance, in this case, where money, okay, just in terms of time, not in terms of any other variable. And to get this, okay, you may have to use a simultaneous equation, okay, so that you isolate it to just one variable. We'll do one like that now. Okay. A couple of basic formulas you're going to need to know in this exercise. If you don't know this, I'm a bit worried. The area of a circle is pi r squared, if that's your radius. And the circumference is 2 pi r. We're not going to give you those formulas. We expect you to know that. And hopefully you know that the area of a rectangle is length times breadth, and the perimeter is 2 length plus 2 breadth, just the distance around the edge. So your second step, okay, is going to be this. So now you've got an equation in terms of one variable. So say we had another situation where you're plotting area against of a rectangle, for instance, against length of a rectangle. And you had some equation. So you had area as a function of length. For example, I just made up a random thing here. Say area was minus 4L squared plus 2L plus T for some shape, right? Okay. The key idea is this. Once you've got an equation in terms of one variable only, okay, the maximum is going to occur when the derivative, okay, so normally I'm going to write it as dA dL. When dA dL is equal to 0, okay, sorry, wobbly desk again. Okay, so you're going to do that. That's going to be the basis of your equation. Maximum occurs when the gradient is 0. Think of the graph, right? Maximum when the derivative is equal to 0. Then you're going to solve for L. So this was a graph of length against area. We're trying to find the maximum area. Well, first of all, we'd have to find the length. We're going to find the independent variable first. Okay, you're going to solve for the independent variable, okay, by using this principle over here. Once you've got the value of the independent variable that maximizes the dependent variable, okay, Once I've got x, how did you find y? Same idea. You sub back into the original equation. So you may have to sub back into the original equation if the question says, go find the maximum area. If it says, find the length, which gives you the maximum area, you'd stop there. But if they said, what is the maximum area? Well, you'd first have to find the length, which gives you maximum area. Then you'd have to sub back into your original function in order to get the maximum area. Okay, right. So that is that. And we're going to, first of all, to do this, we're going to look at exercise 6.10 on page 267 of Mind-Born Maths. So if you get your textbook there, and we're doing question B. And the question says, a toll road company is planning to build a picnic site along a major highway. It is to be rectangular in shape with an area of 5,000 meters squared and is to be fenced off on the 3 adjacent sides adjacent to the highway. Let the length be x and the width be y. There's a shortcoming in this question. They should have really added this bit over here, okay, to stop any ambiguity. Okay, let's just say that the length is adjacent to the highway. Okay, the length is adjacent to the highway. If they're going to ask a question like that, that's what you're going to have. Right. So they break it up into steps, and they say find the total length. Show that the total length is given by this formula. So let L be the length. L is going to be the amount of fencing that we need when you circulate this. They said let L be equal to that, and then find the least amount of fencing that will be needed to complete the job. Right. Now, we break it up into steps if we wanted it to be a kind of either a tough section A question or an easy section B question. But if I wanted to make it a bit of a challenging section A question, section B question, I would just change it to one question and not give you any steps. And I'd say find the least amount of fencing required to complete the job of fencing this. Okay, and let L, let's say, be equal to the total fencing. So I'm going to break all of those 3 parts in the question into one step. Okay, so the first thing is they said let the length be equal to x. Okay, so there's the length. And the length they said was adjacent to the highway. That's okay. And then the breadth is going to be y. Okay. So if we were given one question, okay, what's the objective here? You want to minimize. So you want to have the maximum area, okay, in order to, and that will, well, the area has to be that, okay, and we want to minimize the amount of fencing to reduce costs. So we want to minimize L in this case. We want to find a minimum value for L, okay, and a minimum occurs when the gradient is equal to 0. But as I said in the summary just now, your first step is I need an equation of where I express L in terms of one variable only. Well, I could express L in terms of just y, or I could express L in terms of just x. Doesn't matter which one. Let's just try express L in terms of x. Could be y, could work to give you the same answer. Okay. So the first thing I need to do, step 1 always, is you say to yourself, what are you trying to maximize? In this case, or minimize? Let's try this. I'm trying to minimize L. In order to do that, I need an equation for L in terms of one variable, where L is the distance around the edge. So first of all, what is the length equal to in this shape? The length, L is the amount of fencing I need. Well, the amount of fencing you need, you're not going to fence along the highway. The amount of fencing you need is going to be, if you're a little ant, here you go y plus x plus y. That's your total amount of fencing for the ant to get around. Okay, so in other words, your length is equal to 2y plus x. Right, so now I've got a formula for length, the amount of fencing that I need. Okay, so I've got a formula for the amount of fencing I need. What's the problem? At the moment, this is expressed in terms of 2 variables, so you can't differentiate. But what else do I know? I know that the area of this shape over here must be fixed at 5,000. Okay, so your area is equal to 5,000 meters squared. And what gives you the area? Well, length times breadth is the area of this shape. Even though there's not another side, it doesn't matter. It doesn't affect the area. So therefore, x times y is equal to 5,000. So now I've got 2 equations. Okay. We could now go get length. I need to get length in terms of one variable. So I could either get it in terms of x or in terms of y. It wouldn't matter. I said we're going to try to get it in terms of x. To try to get it in terms of x, I need to get rid of the y. So I'm going to use the fact that if xy is 5,000, y is equal to 5,000 over x. So let's use that. as equation 2, right? So I've got my two equations. How do I solve? I sub in simultaneously. So I'm going to sub 2 into 1. When I do that, the net effect is that you're going to get rid of all the y's. So then you're going to have the amount of fencing in terms of one variable only. So if I sub 2 into 1, I get length is equal to 2 times 5,000 over x, okay? 2 times 5,000 x plus x, right? So we can simplify that. 2 means 2 over 1. So the length is equal to 10,000 over x plus x. Now, for a maximum or a minimum, what's got to happen? Okay, the amount of fencing, sorry, F is, I wish I'd called this F instead of L. The amount of fencing we need is given by that formula over there in this particular case, 10,000 over x plus x. Right, now you need to find, okay, you need to go and maximize that, all right? So fence is equal to 10,000 over x plus x. Okay, I always just, yep, I'm right. Okay, now to find the maximum of that, okay, what are you going to have to do? Well, a minimum of that, sorry, the minimum amount of fencing is going to occur when the gradient is equal to 0. So I've got a graph of x against L, if you want to think of it like that. The minimum is going to occur when the gradient is 0. So I want to know where dl dx is equal to 0. If this is x, that's L, and the gradient I can express as dl dx, or you could write L dashed if you wanted to. I want to know where L dash or dl dx or something like that is equal to 0. So I'm going to have to differentiate this equation, okay? And you should know that in order to differentiate, I can't have any variables in the denominator. So L is going to be equal to 10,000 x to the negative 1 plus x. If I move a power up, what happens? The sign of the, it's just it's a single term, so I can move the power up and the sign of the exponent changes. Now I want to know where the gradient is 0, because that's where the minimum is going to occur. So I want to know where dl dx is equal to 0. So in other words, times it out, where negative 1,000 x to the minus 2, okay, the derivative of x is 1, plus 1 is equal to 0, right? Okay. Okay. So I'm right. So I want to know where that's equal to 0. So in other words, if I'm going to solve this, well, let's make our life easier. I'm going to have minus 1,000 over x squared, okay, minus 1,000 over x squared, okay, plus 1 is equal to 0. So times by x squared, I get minus 1,000 plus x squared. I times both sides by x squared, as long as I write x can't be 0, which we know. So I get, therefore, x squared is equal to, this is 10,000. Okay, it's 10,000. Okay, so I get x squared is equal to 10,000. Okay, so x is going to be plus or minus root 10,000, but x is a distance, so x can't be negative. Okay, so x is going to be equal to the square root of 10,000, right? Okay, and we can go work that out if you want. Square root of 10,000 is going to be 100, right? So x is equal to 100. So when this dimension is 100, okay, then you're going to maximize, okay, minimize the amount of fencing that you need. The question said to us, what is the least amount of fencing that you need? If they said to me, what are the dimensions that you need? Well, then the length would be 100, and y would be 5,000 divided by 100. They didn't ask this, but if they did, 5,000 divided by 100 is going to be equal to 50. So you'd have 50 there and 50 there. So the dimensions will be 50, 50, 100, right? Okay, and that would minimize the amount of fencing in order to get an area of 5,000 meters squared. Okay. Right. Yeah, we do need to find that. Sorry. Okay, they said go find the least amount of fencing. So I've got now that's equal to 50, that's equal to 50, that's equal to 100. So the one way you could have done it is gone to find y over here. So sorry, I'll go over that again. y was equal to 5,000 over x. We had that over there, but we know that you get a maximum when x is equal to 100. So maximum happens when x is equal to 100. So we know that y is 5,000 over x. So I'll replace x with 100, and 5,000 over 100 gives us 50. Okay, so that's the one way you could do it, and you could say, right, now that's 50, that's 50, that's 50. The question is, what is the least amount of fencing that we need? So the least amount of fencing, okay, is going to be equal to 50 plus 100 plus 50, which is equal to 200 meters of fencing is what you're going to need. However, the other way you could have done it is you had a formula over here for the amount of fencing that you need just in terms of x. So you didn't have to go find y. You could have taken this x is equal to 100 and sub it into there, and you'd get length is equal to 10,000 over 100, or replacing x with 100. Okay, plus 100, and 10,000 over 100, okay, is 100. So you get 100 plus 100, which is equal to 200. So the steps, okay, the question was, what is the amount of fencing, the minimum amount of fencing I needed in this scenario? Okay, so your first thing is you say, what are you trying to maximize or minimize? In this case, it was fencing. In order to do that, I needed a formula for L, but in terms of one variable only. To do that, I used simultaneous equations. I used the fact that L was that, and that using area, I got y was equal to that. Sub that in, okay, and I ended up, I went from there to there, okay. I replaced y with 5,000 over x. So y was equal to 5,000 over x, and I got an equation, this is a mess, okay, and L is equal to 10,000 over x plus x, right? Okay, so then I had an equation in terms of one variable. But to get a maximum, what has to happen? The gradient is 0. So the maximum happens, the minimum in this case, sorry, happens, okay, the minimum happens when, in that scenario, when the derivative is equal to 0. So when 10,000 x to the negative 1, I had to change the format, plus x is equal to 0, okay, differentiated, and I solved from there. Okay, quite a lot of work going on. Normally they're going to break it up into steps for you. Right. Next question. Okay. And again, it's question E. Okay. I'm going to break it down into, I'm just going to give it to you as one question. You can go look how the textbook breaks it up if you want to. And question E says this. They give you a whole long speech. You've got a tablecloth, a needed design, blah, blah, blah. On the two wide sides of the rectangular placemat, two white semicircles, and then we've got some pretty decorations. That's the shaded region. Okay. It says to you that the length has to be fixed at 100, but this can vary. Okay. So first of all, the question says, okay, show that the shaded region is given by that formula over there. So I've got to find a formula for the shaded region. And this is usually how they break the questions up. So the question is show that the shaded region can be given by that. But let's just say it was like an end of a section B question. And they said to you, bearing in mind that this can vary, and we're going to call that X, okay, and the length is fixed at 100 of this tablecloth, okay, and they say to you, what is the maximum area of the shaded region under those criteria? That's fixed at 100, and that is equal to X. How can I maximize the area of the shaded region? Okay, so first of all, if they're asking you to maximize the area of something or minimize the area of something, what's your first step? You need an equation for what you're trying to maximize in terms of one variable. So the area of the shaded region, okay, let's try to get that. Well, the area of the shaded region, if I think about it, is going to be a rectangle, the whole rectangle with dimensions of 100 times x. And then you're going to chop out the white bits, which are two semicircles. And two semicircles make a circle, right? So you're going to chop out a circle. I literally do maths like this. I draw the pictures. And in that circle, well, if I'm going to work with area of the circle, I need to know the radius. And how could I figure that out? Well, this distance over here is x, okay, which is the diameter. So if the diameter is x, the radius must be half x, okay? So I've got a circle. To find the area of the shaded region, I'm going to take out the whole rectangle and cut out the two semicircles which make a circle. In that circle, the radius is equal to a half x, right? So area, I'm going to call it a of x. It's a function of x. what's the area of that thing? It's 100x minus the area of a circle is pi r squared, right? So it's going to be minus pi, and the radius is a half x, which is the same thing as x over 2 squared. So a of x is going to be equal to 100x minus pi x squared over 4. So my first objective is achieved. Okay, I've got the area in terms of one variable only. Okay, so this, by the way, is a negative parabola, negative pi x squared over 4. So I've got a graph of x against area, which tells you I can maximize, okay, the area in terms of x. So I'm looking for this point over here. So the first step is I want to find the value of x, which maximizes the area. Then I'm going to sub back into this equation over here in order to get the maximum area, right? So that's your formula for area. So when's the maximum going to occur? The maximum is going to occur, if I think of a graph, when a dashed of x, okay, the maximum will occur when a dashed of x is equal to 0, right? So I'm going to differentiate this thing. Remember, pi is a constant. Just leave it like it is, right? So the derivative of this thing, well, the derivative of 100x is 100. The derivative of that is going to be minus 2 times pi over 4, just using your basic rules, times x, right? That differentiated. Minus 2 over 4, which simplifies to 100 minus pi x over 2. So now I've got to go solve that equation. What is this going to give us? This is going to give us the value of x, which maximizes the area, right? So if I solve, I get, therefore, 100 is equal to pi x over 2. So 200 is equal to pi x if I times by 2. So the maximum is going to happen when x is equal to 200 over pi. So the maximum will happen when this x value here is 200 over pi, okay, which in this graph is over here. So I've got the x coordinate, the horizontal independent coordinate, which maximizes area. So that's 200 over pi. Okay, you can round that off now, but it's better to always leave it at the end because I haven't answered the question. The question is, go find maximize the area of the shape. What is the maximum area? So to find the maximum area now, okay, the maximum area. So what are my steps I've gone through? You're asked to maximize the area of the shaded region. What's your step 1? Get a formula for area in terms of one variable. I did that. Then I said a maximum will occur when the derivative is equal to 0. Solve for the independent variable. If they ask you to now go find the maximum area, I'm going to have to substitute back that back into this equation 1 over here. So the maximum is going to occur when x is equal to 200 over pi. So I'm going to get a of x is equal to 100 times 200 over pi minus pi. Okay, x is equal to 200 over pi, and you square it. I've replaced every x with 200 over pi. And if you shove that into your calculator, I'm going to cheat and look at the answer. You should get an answer of, okay, chuck that into your calculator, and you should get an answer of 10,000 over pi. 100 times 10 over, yeah. Yep, you should get 10,000 over pi millimeters squared. 10,000 over pi millimeters squared. And to make more sense of that, okay, we can go work that out on your calculator. And I go 10,000 divided by pi, okay, equals, and you get 3,183, let's do to the nearest millimeter squared. That is going to be the maximum area of the placemats, a maximum area of the shaded region, okay, in the given conditions. So the question said go maximize the area of the shaded region. Okay, the maximum area of the shaded region would be equal to that over there. Okay, 3 steps. Get an equation for what you're trying to maximize in terms of one variable only. Sometimes you'll have to be used simultaneous, sometimes you won't. When does the maximum occur? When the gradient is 0, in other words, when the derivative is 0. Sub back into the original to get the dimensions of what you're trying to maximize or minimize. Okay, we'll go to a live lesson now, and we're going to go do a few more of these things. Okay, guys, have a good one. Ciao.